Start the recording. All right, okay. Okay, good evening, everyone. Good evening again for the next session, which is the week two for basics of semiconductor microwave devices. I'm Shazan Bhatt, and as per the protocol, we have to introduce ourselves every time we hold this session. I'm a PhD student at IIT Bombay and working in applied quantum mechanics. So this course, which is Semiconductor Microwave Devices, is being offered by IIC Bangalore, and the course instructor is Professor Digvijay Nath from IIC Bangalore. What we are going to cover today is a little bit more involved session than the previous one, but the basics are always going to remain same. So if we talk about the first one, which we covered in the previous section, which was the brief introduction to all of the RF systems, as well as the applications and the historical overview of the RF or the radio frequency, including the microwave frequency devices. So that was just a brief introduction. Now you're going to get more involved into the physics aspect of it. Now you're going to study what are those devices, how you can understand the energy band diagram, how you can understand the band structures. Maybe the band structures is not more involved in it, but you have to understand the more in-depth physics of it. So for that, I have made a just brief outline of what we are going to cover today. The outline will be for the today's session will be we might be able to cover the energy band diagram, the some of the junctions of the physics. What are the different junctions? Uh, what are the different variations of the energy band diagram with respect to the different materials used in making those particular devices? Whether you use gallium, whether you use arsenic, whether you use indium, they are going to have their implications in the energy band diagram. So these are just the overview of the topics I will be trying to cover, maybe starting from the basics and then going into the complex things slowly and gradually. You might be remembering from the previous lecture why I talked about a little bit about the band diagram. I talked about briefly about the band diagram, and I told you that that is going to be the one of the key aspect of understanding these devices because everything is particularly in this, it comes from the electrostatics. If you know how the electrostatic equations work, if you know how the charges work, if you know how the electric field work, if you know how the potential work, how you can make the potential profile, then you can know how you can make the energy profile. Then you basically know everything about what is happening inside the device. Because if you know charge, let's say, let me denote the charge as rho of x. Let's denote this dimension as x. If you know a charge density inside a device, then you can always integrate it in order to obtain the electric field as a function of x. Whenever I will show this arrow over the E, that means electric field, which is a vector quantity. And if you know electric field, then you can always compute the potential, which is a scalar. If you know potential, you always know the energy, E, as a function of x, which is means electronic charge times the electrostatic potential. And if you know energy, you know what is happening to the electron, because that this is the electrostatic potential energy of the electron. Electrostatic potential energy of electron. So whenever you draw the energy band diagram, be it any energy band diagram, be it in case of a simplistic PN junction or a MOSFET or a MOSCAP, whatever you draw, it is always the y-axis is always drawn as the electron's electrostatic potential energy. Okay, so let's assume you have a PN junction. You have a P on this side, you have N on this side. That means you have doped this side with Nd, which are donor type impurities. You have doped this side with, let's say, Na, which are acceptor type impurities. As a result of this doping, you have a positive ion and an electron, you have a negative ion and a hole on this side. Okay, now due to imbalances of these electrons and the holes, this electron will like to go to this side, this hole would like to go to this side, and this is the situation overall that is happening in a basic layman sense. Okay, so what happens because of this motion of the carriers is this thing. Because of this motion, near this particular junction, which is shown as a dashed line, you have the positive ions coming up from this side, and you have a negative ions coming up from this side, because you see that particular motion will occur at this particular metallurgical junction of this device. And once the electrons and the holes will satisfy each other in terms of when the electron will go from this region to this region, the hole will go from this region to this region, electron hole will recombine, they will satisfy these bonds, and only thing remaining will be these positive immobile ions. These are immobile ions, immobile ions. And you know that this particular thing is called as W depletion. This is the depletion width. And it gives rise to the formation of this space charge region, which is the depletion region, or transition region, or space charge region. It has been given different names in the literature. And now life becomes simpler. Why? Because if you know this charge, particularly this immobile charge, now you know whenever there's a charge, it sets up the electric field. In this case, if it's a positive charge, the electric field comes out from a positive charge. You know from your basic physics, the electric field lines come from a positive charge and they go inside the negative charge. Okay, that is just the basic physics. That means electric field will look in this direction. That is going to come out from a positive charge and going to terminate on a negative charge. So this will be the direction of electric field. As a result of this electric field being set up, you know that force is equal to minus q times electric field. The force on the electron in presence of an electric field is going to be equal to minus q times E, just from your basic physics. Okay, you might know about whenever the electric field whenever the electron is in the presence of an electric field, let's say electric field is in this direction, the electron is going to move in this direction, and the force applied on this particular electron will be minus q times the electric field. If there is a magnetic field present, then the overall force will be equivalent to the electric force plus the magnetic force. Electric force will be minus q times E plus magnetic force will be q times V cross B, where B is the magnetic field. Let's say the magnetic field is going inside. So this is something called as Lorentz force. That is just from your basic physics, just trying to recapitulate whatever you are knowing from the basic 10 plus 2 level. So that is the particular force which electrons will be trying to go opposite direction, and the holes will feel the same force in the same direction, because we consider holes to be positively charged. Okay, so that is going to be the scenario. Overall, the electrons are going to move in this direction, holes are going to move in this direction. The the overall current is going to be in this direction, particularly because the holes are moving in the opposite direction. Okay, so the convention is that you take the direction of the current to be opposite to that of the electron motion. Okay, and it is same as that of the hole motion because it's a positive charge. All right, so whenever you have to draw the space charge diagram of it, I told you in the previous session that whenever I will go fast here because you have a charge density here. Let's consider this direction as x. Then let's consider this as abrupt junction. What is meant by abrupt junction? Abrupt junction, because this is mentioned in one of your assignment problems also. Abrupt junction means that this particular junction terminates abruptly. So there is an abrupt termination of this junction. If it would have been not abrupt, the actual junction looks like something like this. There is a spread. This is the actual how the actual junction looks like. Not like this. The actual junction logo looks like this. There's a spread. But if it is abrupt, then it looks like a black one. It looks like a black color. It abruptly finishes at this particular point. Let's call it xn. Let's call this as minus xp. Okay, so that this overall xn plus xp is equivalent to W depletion, which is the depletion width. So I'm just talking about a homojunction device. Homojunction device. Homojunction, which you have been told from previous classes. That means this particular can be maybe silicon, this may be silicon. Let's say this is having energy gap Eg1, this is having energy gap Eg1 also. That means both the energy gaps are same. Okay, so we're talking about a homojunction device here. Okay, then I told you that if you know about the potential profile, you can actually integrate it in order to obtain the electric field, and the electric field will look like this ramp function, which is the linearly varying function, and this is the maximum electric field, which will be exactly in the middle of this region, exactly in the middle of this particular region, this particular region. So at the middle, the electric field is going to be maximum. Now, if you integrate this particular thing again, because You can write potential as minus integral of E dot dx from x, maybe x minus xp to xn. You can integrate it and you get a parabolic type of function. And this is v as a function of x. Then you can write energy, which is electrostatic potential energy of electron, as minus q times v of x. That means you can just invert it and you will be getting something like this. And you have this particular figure, which is basically the conduction band of this p-n junction. So that is what you show in the energy band diagram. This is the energy band diagram of p-n junction. This is ec, this is ev, and oh god, what happened? Just a second. So is my screen visible? Well, just okay. Let me just move it from this side. Share screen. Continue. Start broadcast. So I messed up here, I think. All right. Okay, so I guess it's visible now. So what happens is that you have a common Fermi level. This side is n-type, this side is p-type, because you see that but this particular difference, the difference between the Fermi level and the valence band is less, and the difference between the conduction band and Fermi level here is less. That means this particular side is n-type, this is p-type. So this is the particular depletion region I'm talking about, and this particular figure refers to, it comes directly from the electrostatics that we have talked about. Now this is the particularly the case when EG1, these particular band gaps are equal everywhere. You see that there is no variation in the band gap. If this is EG, this is also EG, this is also EG. The band gap remains same everywhere. And also we have taken this both of these two materials as similar band gap material. Okay, let's call this as silicon, this as silicon. Now what happens in case of a heterojunction device? Heterojunction device. It turns out that little bit there's a difference in the heterojunction, how you draw the band profile of the heterojunction device, but the same rules are applicable in case of a heterojunction device. Now, if you let's say have a heterojunction device, let's say a heterojunction device like this, which is having the band gap EG1, and let's say there is another material on the side which is having a band gap EG2, and clearly you can see that EG2 is greater than EG1. Okay, let's say this, for example, this is a p-type, nearly p-type material because the difference between the Fermi level and the valence band is less here. And let's consider this to be as maybe n-type. Let's say this is n-type. So now what is going to happen? You know that the motion of the electron is always from a higher Fermi level to a lower Fermi level. The Fermi level is basically the reference which indicates where the electrons are going to flow. So it's just like water in a bucket. If you have one bucket, if you have another bucket, and it's separated by something, and if you have, let's say, water in this bucket up to this level, and if you have water in this bucket up to this level, so if you, let's say, open this particular thing and water will start to pour from this end to this end. If you just tilt the particular buckets, and the water is going to go from this end to this end, because naturally the water is having higher, I should say, gravitational potential energy here, gravitational potential energy. Okay, because it's having much greater height in this particular bucket, so it will try to equalize the heights on both sides. So the scenario will come that both of these heights will be equal. That is the equilibrium scenario. So this particular top is exactly the Fermi level. So this is the Fermi level, what we are talking about. It's the same as what happens with the electrons. So electrons try to go from this higher Fermi level to the system where there is lower Fermi level. And at equilibrium, they try to align each other. Now, how you draw the band diagram of this particular thing? You need to consider, first of all, these particular points on this dotted line which mark these particular original conduction and valence band. So, and here original valence and conduction band are marked as dotted lines. Why it's done? Because you see that both of these are having different band gaps. Now they no longer have the same band gap. Otherwise, if they are having same band gap, it makes our work easier. Now, what is going to happen? I told you that the electrons are going to move from n-type towards the p-type region. That is, the motion of the electrons will be in this direction. So what is that going to happen? That is going to happen. This particular Fermi level is going to go down. This particular Fermi level is going to go up. And in equilibrium, the overall Fermi level will be flat. This is in equilibrium. Equilibrium. Overall Fermi level is going to be flat. Okay. There'll be in equilibrium, there'll be no net motion because now it's flat, just like water level. When it becomes flat, water doesn't move from one end to other end. Similarly, electrons don't move, at least in layman's sense. Okay, so when it does so, in doing so, when think about it, when this will come down, the this particular line which is shown in the green, it will also come down, but near this particular point, it's going to cause upward band bending. Okay, because it is just like squeezing those bands down. So overall, if I extrapolate this particular dotted line here, it's going to look like something like this. Oh God, it's going to look like something like this. Okay, and here it's going to look like something like this. Fine. This is on this side. Now on this side, this particular Fermi level went up. That means it is going to, and it was above it, and that means it's going to if this particular thing, let me show it here. If this particular thing goes up, then that means it's going to squeeze it further, and this is going to look something like this, and this is going to look something like this, and you have to just join these particular things. But you have to make sure that in the bulk region, which is this bulk region, the bands are flat. There is no significant change in the bands. Here, the bands are flat. It is mostly at this particular region the change happens, the bending happens. Okay. Inside the bulk, you have to make sure that it remains as what it was. It is p-type here, it is n-type here. Now, at this particular location, the maximum change happened. You see that there is now bending, a weird shape of bending happening. And now there are different names. Now this particular thing is called as delta EC, which is the conduction band offset. This thing is called as delta EV, which is the valence band offset. Okay. Now you can play with these particular things. Now you can do multiple things. Maybe you call this, let's say, let's call this as this particular thing. This particular thing is called as the built-in voltage. Let's call it VB1. This particular thing is called as VB2, which is the built-in voltage again. This will be this will be, let's call this as let me rub this. This particular thing is also bent here, so this will be VB2. This will be exactly VB1 because the bending is on the same side. So these are the built-in voltages. These are the built-in voltages. Just like in a PN junction. This is the built-in voltage in the PN junction. And the built-in voltage in a homo junction, you knew from the basic device physics, we used to compute like Na Nd divided by Ni square. This was the relation which you computed using Poisson's equation, if you remember, in the homo junction type of device. Homo junction type of device. But here you don't have any doping. Okay, so you don't have a acceptor type impurity, or you don't have an donor type impurity here. Okay, so here different rules are followed in order to obtain these particular, I should say, what is called as the built-in potentials. So that is basically one of the problems in your assignment section. So you remember that this particular gap is basically the EG. Let's call it EG2. This particular gap is EG1, and this particular difference, which is the EF minus EV, is something called as Fermi potential. Fermi potential. And you know from your basic physics is EF minus EV is KT over Q ln of maybe NV divided by let's call it some concentration, electron concentration. Okay. Uh, let's call it some electron concentration n. Basically, this will be, if it is p type, then it will be Na type, or maybe some certain number of concentration of the whole. So let's call it p. You can write it as p, because if you consider fully ionized maybe impurities, then you can consider it as p. Then similarly on this particular side, this particular difference, which is EC minus EF, that will again be equivalent to KT by Q ln of NC divided by maybe N, where these are density of state, these are something called as effective density of state concentrations, or whatever you call them. And these basically come from by considering the effective masses and other things. But for the simplistic scenario, you can consider them as constant. Yeah, you have a question here. Where I can see a question? Yes, you have a question. I'm not able to hear you. You have raised your hand, but what's your name? Bhavani Satya. You have raised your hand. Do you have a question? Okay, I guess this is a mistake. Okay, just take care of it. All right, so we can compute these particular things. Now, what we do a cool trick here in order to compute the effective, or I should say, built-in potential. How do you calculate the built-in potential? You select a point on the band diagram and you go in one direction, then come down the other direction. And if you go up, you consider that as positive. You go down, you consider that as negative. That's the simplistic rule. It's a cool trick. How it's a cool trick? It's just like you might be knowing about KVL, the overall voltage. Let's say if this is a resistor, this is a resistor, this is a resistor, and let's say this is R1, R2, R3. Let's say this is V. Then you know that there will be same current across. Then that means this will be IR1, IR2, IR3. This is the voltage drop across will be V1, V2, V3, and you sum over all of those voltage. That means V equals to V1 plus V2 plus V3. Okay, this is the overall voltage sum rule, just like in a KVL, if they are particularly in series. Similarly, what you do is that you just sum over all of the voltages in a loop, in a closed loop. It's not a KVL here. Don't try to just kind of compare these two, because it's not a circuit. It's just an analogy I'm trying to make. You go over in a loop, but you have to make a loop. You have to end up at that particular point. If you don't make a closed loop, then you will end up getting a wrong answer. Just like if you in this particular, just like in this particular band diagram, yes. If I can duplicate it, let me see, duplicate. Oh, what is happening today? If I can duplicate, okay, just move all of this. If you can see, let's start from, let's remove this thing. If you, let's say, start from this particular point, then you have to go all together to make a closed loop. You go up, then you go up by this particular thing, then you maybe go up by this particular thing, come here, then you go maybe down by this particular thing, go up again, and that means you reach back to this particular point. Okay, this is the particular line you choose, and it formed a closed loop. If you just form this particular closed loop and sum over all of the voltage you have encountered in between, then what is going to happen is that you are going to compute the overall, let's say, the built-in potential. But you have to consider you always form a closed loop. If you don't consider a closed loop, then it's going to create a problem. That is also basically one of the problems in your assignment. Let's consider this heterojunction. Let's consider, I have an example here, maybe that will make our life easier. If this is, let's say, a heterojunction like this, let me draw it like this, and you have a Fermi level here. That means this is again a p-type. This is some heterojunction. So, okay, let's say this is ND1, and this is maybe you call this as conduction band offset delta EC. This is particularly, this bending is QV. Let's call it QV2, which is the built-in potential. And let's call this bending as QV1. And this particular thing is also, let's call this as EC minus EF. Okay, so and we are also given, let's say, this is EF minus EC. Now, th think about this particular thing. You start from, let's say, any point. It doesn't matter where you start. You can start from here also. It depends upon what is the problem given and how you are going to approach that particular problem. Okay, if you start from this particular point, you can go up, then you can go around in a loop, but you have to end at this particular line or a particular voltage point or energy point. Okay, you can select any point. Let's, for the simplicity, assume this point. Then you go up again, and consider the convention. Whenever you go up, you consider that as positive convention, and you sum up those voltages. If you go down, you consider that as negative. This is the convention we are going to follow. You can do the opposite, but you have to maintain the convention. You can consider up as negative, down as positive. You will arrive at the same answer. At the end, you have to sum up all of the voltage in a loop. Okay, so whenever you just go up in this particular band diagram, you have to sum over all of the voltage to equivalent to zero. Okay, now what you do, you go up one. Let's consider from the beginning. You 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 go from this particular point, you go up, which is equal to the which is the difference, which is the Fermi potential, this particular thing. Then you go from this and you go again up, which is equal to QV1. Okay, then what you do, you are now on this line. You have to move on to the other side. Now you go down by, let's say, this particular thing, which is basically the delta EC, which is the conduction band offset. Okay, and while doing so, now let's consider this as here. Maybe this might confuse you. When you, for example, go down this particular thing, then you have reached, for example, you have reached this particular point. Now, for example, if you go down here, you can even go down to the other point of the valence band, and then come up here, and then maybe again go up here. But you have to make sure that you always end up in a loop. Okay, and the loop gets closed in a it's like a closed fashion. Okay, now once we move it in a particular loop fashion, we can sum up all the voltage in a path. Let's consider first path. Let me just draw a schematic of this. This is the first path, which is maybe from this Fermi level to the conduction band on the left hand side. Then you went up again, which is basically QV1. Then you move to the other side. Okay, then you went down as the delta EC, which is the conduction band offset. Okay, then you went again overall down, which is the let's call it 4, which is equal to the band gap of this on the other side. Then you went up again, which is, let's call it 5, which is basically equivalent to going up to the Fermi level point. And then you went up again, which is basically equivalent to the 4, which is basically equivalent to V2, the built-in potential. Okay, you sum up all these voltage. Now let's do it one by one. You can actually gather it from by writing the equations. So when you write the equations, the first thing when you went up, that difference was equivalent to KT by Q ln of N, no, what is this, NC divided by P. Let's call this P. This is not P, this is ND. Okay, this is ND. Okay, so this is the first thing you went up. Then you went up again equivalent to V1. Let's write everything in terms of the voltage, because this is all in voltage. So QV is energy, only V is voltage. Just remember this. So when you do it, then you went down. The down arrow you considered as negative. You went down as delta EC divided by Q, because it has to be in voltage. Okay. Then you went up, which was equivalent to the built-in potential. All right. Then you went again down, which was equivalent to the band gap divided by Q, just to make it in terms of the voltage. But this is EG2, just to make sure, because this particular thing is EG2. And then you went again up, which is equivalent to the Fermi potential on the other side, which is ln of NV divided by NC, whatever you call it. Yeah, NV over, not NC, let's call it P. Let's call it some concentration. And now what we have? We have a equation which sums over in a loop, it sums over to zero. Okay, because you're not externally applying anything. If you will externally apply anything, then it's a beautiful thing that you don't have to sum up equivalent to zero. Then there will be difference in the Fermi level, but we are all considering it in equilibrium case. So whenever you consider this in equilibrium case, you will sum up to equivalent to zero. Now, what do we want from here? We want V1 plus V2, which is the built-in potential. So you keep V1 plus V2 here, and you take all of the things on the other side. So when you do, which is equivalent to VBI, you do this thing, you get V1 plus V2 basically is equivalent to maybe KT by Q ln of NC divided by ND, and maybe minus EG2 divided by Q minus delta EC by Q plus not this is not the sign. This will be plus, this will be plus, and this will be minus KT by Q ln of NV divided by P. So this is the overall view how you compute the built-in potential. Now you should be knowing all of these particular parameters. Now there is one more aspect in this particular figure. Whenever you draw this particular band diagram, you always have to draw the something called as vacuum level. That is the most important aspect, which maybe most of the people miss. Whenever you draw this particular diagram, you have to draw the vacuum level of it. Vacuum level is something like a reference level, where let's say if you consider electron going from this level to the vacuum level, E vacuum, then it's almost as if electron is free. Now it's not under the influence of any forces coming from the crystal. It's not in a potential, electrostatic potential. It's now free. It's behaving as a free electron. A free electron has its certain properties. We won't discuss that here. What is happening to a free electron? It's just like a plane waves moving inside the crystal system, but it's still in the crystal, but it's under the not under the influence of the crystals. Then whenever you do certain things, you have to consider this particular difference in a semiconductor is basically called as electron affinity, the difference between the conduction band and the vacuum level. And this is also electron affinity on this side, on this particular side. And whenever you draw this particular figure, you have to consider that electron affinity is a material property and it doesn't change. It's just like a band gap. It always remains same no matter what you do. You cannot change the you cannot by moving the charges here and on the one side to other side, you cannot change the intrinsic material properties. Okay, you can change it maybe by giving some external forces, but not at equilibrium. You have to make sure that whenever you draw the band diagram, the band gaps have to remain same, the electron affinities have to remain same. Even the work functions have to remain same. Okay, they are the intrinsic properties of the material. The work function is basically the difference between the Fermi level and the vacuum level. That is called the work function of semiconductor, represented as phi s. Those are from the basic device physics. Okay, and that means this particular point and at this particular point, this particular difference, which is the electron affinity of semiconductor 2, should be exactly equal to what it is inside the bulk. At this particular point, blue, and this particular difference is the electron affinity of semiconductor 1. It has to be same. And you can see that this basically chi s2 minus chi s1 will give you this particular difference, which is this. It can give you this value also. So there are n number of options to evaluate these particular variations in the band diagram. It just depends upon your thinking, how you think of a particular band diagram. Otherwise, there are thousands of ways of doing this or solving this particular figure. Let me just take this one more page here. And this is about the band diagram. What is next I want to cover. Now, this is one part of it. Next part is what we consider as maybe something called as abrupt junctions. This was an example of an abrupt junction. Abrupt junction and a graded junction. Graded junctions. Okay. Now, what is the difference between these two, and why are these two particularly important? Now, this for example, this particular thing was a result of abrupt junction. Abrupt junction. Abrupt means it's a sudden junction, and you can see this particular junction here, which is this particular junction. It's just like an abrupt change in the potential. Okay, so this whenever this type of potential gets formed, it's called as abrupt junction devices. And if you don't have an abrupt change, let's say you, for example, take maybe aluminum arsenide, which is maybe a huge band gap material of the order of 3.4 electron volt, and you take, let's say, on the other hand, maybe gallium arsenide, which is a small bandgap material of the order of 1.4 electron volt. And if you go in this direction and you start to grow it layer by layer by using certain atomic techniques, you grow and you start to increase aluminum concentration in it. It is actually written as AlXGa1 minus X arsenic, As. You increase X, that means you go from point 1 to point 2 to point 3, so on up to you make it 1. When the X becomes 1, it will be aluminum arsenide only. And you do it in a stepwise fashion. When you do so, you observe that as you increase the X, which is the mole fraction basically indicates how much is the concentration of aluminum in it compared to that of the gallium. Okay, as you increase the aluminum mole fraction, you see that the band gap starts to increase like this, and when it becomes aluminum arsenide, it matches the band gap of the aluminum arsenide. And the fascinating thing happens that this particular thing becomes the band diagram of it, which is very weird. Why it is weird? That means this is the conduction band of it, this is the valence band of it, and this is called as graded junction. It is smooth. There is no abrupt change in the electrostatic potential. Now, why is it weird? It is weird because you can do multiple things with it. If you talk about homojunction PN junction diode, PN diode, this is positive, this is positive, these are positive immobile ions in the depletion region. You know that this is the direction of electric field. That means will electron, let's say, will try to move in this direction if there is internal electric field. But you all know that when the current flows, you are going to apply some forward bias, external voltage. This is positive, this is negative. That means this will be forward biased. Okay, in the forward bias, what is going to happen? You are going to inject electrons from this side. They are going to flow in this direction. The holes are going to flow in this direction again. Because if this is the equilibrium band diagram, this is the Fermi level, then you know if this is QVBI, this is the barrier, then in the forward bias, what you do, you reduce this barrier height. It becomes like it becomes like this. It becomes like this in the forward bias. This is in forward bias. Okay. As a result, electron will move in the opposite direction, hole will move in this direction, and you have a conduction and you have the overall current flow, which is the electron current plus the hole current. Okay. And you know the electron current component is basically the drift current component plus the diffusion current component. And drift current is basically Q times Q, and it's basically charge, it's basically the concentration charge mobility times the electric field. Drift is basically dn, which is the diffusion constant of the electrons, the gradient of the gradient of the electronic charge, the gradient of the concentration with respect to the x. So this is basically the overall current. So this is only the electronic component. The whole component will have will have p instead of n, and will have dp instead of dn. This is the overall current equation. But this is just the homojunction, you know. But you know about it that both of the electric field here, you see that this particular bending, the bending I'm showing in green, both have the same bending. That means the overall direction of electric field is this direction. Why? Because this is the particular slope, and electric field is basically negative gradient of the slope of potential. But what potential? This is just a potential. You need to convert it into energy. And how do you convert potential into energy? You know that energy is minus Q times potential. So you can write potential as minus E by Q. So you can write this in terms of energy. That means electric field will be equivalent to 1 over Q d energy divided by dx. So this is the gradient of the energy band diagram gives you the electric field. Okay, and the electric field here both is in this direction, same direction, whenever the electric field is set up. And that is quite simplistic, from because you have a positive charge here, negative charge here, electric field will be in this direction. But graded junctions have some weird property that you see that this bending here, it is in this direction, and you see this bending here, it's in this direction. They have these opposite bendings in the conduction and the valence band. So what happens because of it? Because of it, At the top, at for the electron, the electric field is in this direction, and at the bottom, the electric field is in this direction. This is the electric field for electrons, this is the electric field for holes. And you know electrons move in the direction opposite to that of the electric field because they feel force F equals to minus Q times electric field. The minus sign makes it to flow in the opposite direction. So if you have an electron here, it will go in this direction, down the hill. Basically, down the hill it will go. And if you have a hole, that will also go in this direction because hole moves in the direction of electric field. Hole is just like a positive charge. So you will have motion of electrons and holes just like this. And you have an electric field which is opposite in directions. For the electrons, it's in this direction. For the holes, it's in the opposite direction. Okay, so that is the weird property. For what you can do with these properties that you are going to study in the near future in the devices, what the graded junctions are basically used for. But in case of a homojunction, that was not even possible. You don't have a different band bending for both of these conduction as well as the valence bands. All right, so this was about the junctions, just a recap about it. Why does it happen? And what is the other part we want to discuss? Maybe we want to discuss about let me check this. Okay, let me check this. Okay, let's discuss briefly about discuss briefly about gallium nitride based high electron mobility transistors. So this is a very quite a hot topic because these high electron mobility transistors definitely are used in RF high frequency applications, let's say gigahertz applications for commercial as well as defense applications. And even today, I should say most of the space applications like ISRO, even NASA, they use these gallium nitride based devices in order to communicate with their satellites. And and I should say most of the devices of all of these gallium nitride based devices because they are very I should say sensitive devices in terms of because they are used for defense applications. So IIT Bombay and ISRO basically together make these gallium nitride devices so that they can use it for their defense applications and tactical purposes. And it cannot be imported from the outside because they don't allow it. So you have to fabricate it inside. So people at IIT Bombay or other maybe IIT Delhi and Kanpur, they just collaborate to make these particular devices. And it's a very tiresome process because it takes a lot of days to fabricate these particular devices at nanoscale. And so what happens is that now we talk about the gallium nitride. So gallium nitride is a it's a binary compound. It's a binary compound which includes gallium and the nitrogen. So it has a unit cell which basically looks like a stretched hexagon. Just like a silicon has a unit cell which looks something like this, maybe a cubic. Maybe you might be knowing about NaCl, which is a sodium chloride. It takes a cubic type of unit cell where the atoms are placed just like this. Similarly, the gallium nitride basically has a unit cell, which is the crystal structure similar to that of a somewhat like a stretched hexagon where the atoms are placed like this. And if you just extrapolate it, you can draw it something like this. You just draw it like this, where these are the atoms of the where these particular atoms. So basically there are two atoms. So you have the gallium, you have the nitrogen. So this is the gallium is the bigger one, nitrogens are the smaller ones. So if you let's say draw it like this, let's draw it for the simplicity. Let's draw it something like this. It's not exactly tetrahedral, but it's just like a maybe you have taken this atom, this atom, this atom, this atom, and this atom. So they are bonded together, and but the gallium is the bigger one, and then it's followed by the nitrogen. And you can see it in the periodic table also. But you know from the periodic table that nitrogen is having more electron affinity. That means it's having tendency to attract the electron cloud towards itself. So that means overall electron cloud will be shared between the gallium and the nitrogen, but will be more towards dominated towards the nitrogen. So because of that electronegativity difference, there is a delta negative charge on the nitrogen and slight delta positive charge on the gallium. Okay, that means the electron cloud is mostly towards the nitrogen. It's mostly towards the nitrogen, and slightly there is positive charge over the gallium. And now because of that, you know that it will set up an electric field now. So now when you consider all of the components of these particular charges, you see that let's say this is the direction of electric field in from positive to negative, from gallium to nitrogen, gallium to nitrogen, gallium to nitrogen, and gallium to nitrogen. And when you draw the direction of the polarization field, you know because the polarization is susceptibility times the electric field. Okay. And whenever you write polarization, you have to consider the electric displacement vector, which is basically the electric field, which is epsilon permittivity times the electric field plus the polarization. So overall displacement vector is something like this. And this basically goes into the Maxwell's equation, which you might be maybe knowing. Basically, integral of d dot ds is equivalent to the charge inside. This is the basic Maxwell equation you might be knowing. This is also the Gauss's law, basically. So the charge inside is the surface integral of this particular electric displacement vector. And the direction of the polarization will be opposite to that of this. So you have to consider the direction as this. And then you have to resolve it into two components, because if the direction is in this direction, if the direction of certain electric field or even the polarization is at certain angle, let's say with respect to this theta, then you have to, let's say, resolve it into p cos theta, and you can resolve it into p sine theta. When you do it, when you resolve it, you see that overall polarization is developed inside this material. Okay, and there will be, because of these negative and positive charges, the overall top of this particular structure behaves as a negative charge. The overall bottom behaves as a positive charge. That means this is slight delta negative, this is slight delta positive. So this is the overall schematic because of these polarization charges. Now I have shown here a schematic of a single structure. There are thousands of unit cells in a structure that sums up, and that gives the overall top layer as a negative charge, overall bottom layer as a positive charge. Okay, that means if you have a gallium nitride based structure, overall the top is going to behave somewhat positive, the overall bottom is going to behave somewhat negative. So this will be slight delta negative, this will be slight delta positive. So this is something called as spontaneous polarization, spontaneous polarization, spontaneous polarization. Let's denote it as delta sigma P, delta sigma SP. So this is something called as spontaneous polarization. And similarly, if you have other materials where you have a huge electronegativity difference between, let's say, one element and another, let's say you have aluminum nitride. And if you consider aluminum nitride similarly, there is a huge electronegativity difference between aluminum and nitride. And it gives rise to huge polarizations again, huge polarizations. And you will see that these polarizations are very important in case of high electromobility devices. And it is these polarizations which basically give rise to something called as electron channel inside these particular devices. Because you don't dope these devices just like silicon and germanium. You don't dope these devices. There may be doping which is unintentional. Unintentional. That means you don't intentionally dope it, but because of certain impurities which may happen at factories, industries during the fabrication, maybe, let's say, some carbon may get diffused into it, or some silicon may get diffused into it. So if that happens, then you have something called as CGAN, you have something called as silicon GAN, and based upon the impurity concentration of carbon and silicon, they may become slightly N-type and they may become slightly P-type, maybe. Otherwise, they are intrinsic GAN. They are not doped. Okay. The other thing is intentional doping. Intentional doping. Intentional means if you by intention dope it with something in order to make it more negative, in order to make it more N-type, more P-type. That is something different. That also you can do here. Okay. But mostly what you do is that you do something called alloying. Alloying. Alloying is, let's say you have a GAN and you start to increase the concentration of aluminum in it. And you represent it as AlX, 1 minus Xg, Ga, and N. And this becomes something called as AlX, Ga, 1 minus X, and nitrogen. So this is called as, while adding this, you have done something called as alloying. And if Al concentration goes on increasing, that means X increases, you have the Eg band gap goes on increasing. That means if you had, let's say, a gallium nitride of 3.4 electron volt, you start to increase X, you start to increase aluminum concentration, the band gap starts to increase and it becomes more of a much greater band gap. And it becomes finally aluminum gallium nitride, let's say at if X is equal to 0.2, and that means 1 minus X is equal to 0.8, which is basically the concentration of these aluminum and the gallium. And if X is equal to 1 minus X is equal to 0, that means it will become aluminum nitride. Okay, so that's what these are all a family of these compounds. You can form aluminum gallium nitride, you can form aluminum nitride, you can form gallium nitride. So these all come because of varying these alloy concentrations, or what you call as varying this aluminum concentration. Okay. So that is the basic fundamental of these particular systems. Now let's go into more of the device aspect. Let's go more towards the device aspect. Let me see what have we here. Okay, this is done. All right. Okay. Okay. So one more thing that is important here is that if you take a, let's say, a gallium nitride based maybe a material, and if you want to grow something like algan here, that means you start to increase the aluminum concentration here. Whether can you do it, or is it always permissible? Well, it turns out it's not always permissible, because what happens is, if you have a gallium nitride, if it has atoms lined up something like this, and if the aluminum gallium nitride has atoms something like this, not smaller atoms, the lattice constant is smaller. Let's say the lattice constant here is A1, and for the algan it's A2. That means A1 is greater than A2. Okay, so what happens? In order to match the lattice, that means this particular should be matched, this particular should be matched, this particular should be matched in order to make the desired bonds near the interfaces. Basically, what happens at the interface? There is a formation of bonds. Okay, but if all of the bonds cannot satisfy each other, then whatever remains are the vacant orbitals. And vacant orbitals are the sites for the electrons to stay. And they give rise to defects, they give rise to impurities, so on and so forth, which is not desirable. Sometimes it is desirable, but not all the time. That means if you have a, let's say if you have a bond here, let's say if you have this bond, and there is a bond, let's say at this particular, if you zoom this particular site, you have bonding like this. You have a, this comes from the algan site, this comes from the gallium nitride site, and you have another bonding site like this. You have another bonding site like this. These are head-on bonds. Let's say what you call as a p and p orbitals if they overlap. Okay, but if there is another orbital here, and it cannot be satisfied by the other orbital on the other side of the algan, then this particular site remains vacant. This remains vacant, and it can host electrons. Electron can sit here. If electron can sit here, it acts like a defect state, which is not desirable. So the fewer these sites are present, the best is the quality of the material grown over the gallium nitride. And the more of these sites, if there are more of these particular vacant sites, the, I should say, bad quality of material is grown over this particular material. So these particular sites, which are called as interface states, they are very important. Not all of these. This particular gives rise to an interface state. So there are thousands, millions of these interfacial states, and you have certain processes in order to terminate these interfacial states. Okay, something called as passivation. You pass the hydrogen gas or the oxygen gas in order to satisfy some of those bonds, because at the end you have to make a bond with this particular orbital. Once it is done, it can no longer accept an electron then, and it will be satisfied. So you can and you can satisfy all of these particular interfacial states, but it's very tricky job to make this particular interface. So that is what happens basically at this particular interface. Now what you have is that you have to match this lattice sites. That means that there should be lattice. There should be no or minimum lattice mismatch. That is the important aspect. So you cannot grow an arbitrary material over this particular over these particular sites. Okay. Now we talked about these particular things. That means if there is the lattice constant of A1 is greater than A2, that means GAN is greater than that of ALGAN. That means this has to slightly stretch here. This has to slightly stretch towards the other end. Something called as tensile stretch, tensile strength, or tensile stress, what you call, or strain. So stress is basically force per unit area. Strain is basically the change in the maybe volumetric. If it's volumetric change, then delta V by V. Okay, that is the overall stress and strain. And from the Hooke's law, you know that stress can be given as maybe some Young's modulus times the strain. This is the Hooke's law, the basic Hooke's law you study from the class 12th. And it turns out that these particular things are not simple quantities. These are basically something called as tensors. When you go to the higher dimensional mathematics, this is basically written as something like stress is equivalent to C tensor time. This is basically a tensor, and this is basically something called as tensor notation times the strain. And these are overall matrices where it's C11, C1, C22, C33, C44, and this is C12, so on and so forth. And similarly, you have this matrix which is epsilon xx, epsilon yy, epsilon zz, epsilon xy. These are the different strain components in different directions of the material. Let's say you have three-dimensional material, then you have this x, y, z. Then this is sigma x, this is sigma z, this is sigma y. Then you have different combinations of it that gives rise to strain in different directions. If it's something called as anisotropic. Anisotropic means it has different properties in different directions. If it is isotropic, then it has same properties in same direct all the directions. It doesn't matter. But mostly these are basically certain complex matrix which are used to basically denote these particular stresses and the strains inside the material. So that's why maybe somewhere the professor might have mentioned an equation containing the C13, C22, these coefficients. They are basically the elastic moduli coefficients, which basically comes from the Hooke's law when you write it in higher dimension notation. So that is quite often used when you do the maybe study about how these materials stretch or how much there is a strain. So that's the common equation which is basically used in all of these device physics. So now what happens because let's say when you have let's say for example when you now grow an aluminum gallium nitride over the gallium nitride. So now you saw here that you have a very mismatch of the lattice constant mismatch slight. You try to reduce it, but you know that A1 is greater than A2. That means there will be certain tensile strain. Okay, and this particular strain limits the thickness of the material which can be grown over the gallium nitride. You cannot make it arbitrarily thick. It's just like civil engineering. You cannot make an arbitrarily higher building over the ground if if the ground cannot support it. If there is a weak base, you cannot create a building of a greater height over it. It is the civil engineering at a nanoscale. You cannot grow the higher thickness of a material over something which cannot support it. If you do that, it will kind of burst or it will kind of it won't be able to this gallium nitride won't be able to support this particular layer. So that's why there's a threshold of this particular thickness which can be grown over the gallium nitride in order to for it to be at least placed over the gallium nitride in a fixed position. Okay, so this is approximately 20 to 30 nanometers for AlGaN, if I correctly remember. These numbers are not important. They can just Google it anytime. You just need to understand the concepts. So if this is gallium nitride, then I told you that the overall top will be positive and overall bottom will be negative because of the spontaneous polarization. So this is spontaneous polarizations. They arise from it. They arise from the polarization and the dipoles which are present inside this particular gallium nitride. And similarly, for the aluminum gallium nitride, we have this particular layer as positive spontaneous polarized, this negative as top layer as negative spontaneous polarized, using the similar procedure. But it turns out there is one more component, which is the piezoelectric component. This piezoelectric component comes because of the stress and the strain. Stress and strain. Because there is a tensile strain because of lattice mismatch, that's why these components come. If you do something, maybe something called as interface engineering or something called as band engineering or let's say thin film engineering, if you do something where you can absolutely make it relaxed over the gallium nitride, you can totally omit these piezoelectric components. But these are still there. These are there in most of the AlGaN which is grown over the gallium nitride. So these components come because of that piezoelectric stresses and the piezoelectric strains. Okay, so piezoelectric you might be knowing if you apply a stress over certain material, the inside orientation of the dipoles takes place in such a way that it gives rise to an electric field. Okay, so that means you apply stress, it gives rise to an electric field. That means electric field means voltage, and its opposite is also true. If you give voltage to certain particular materials, it develops stress. There's something called as inverse piezoelectric. This is piezoelectric. There is another phenomena called as inverse piezoelectric. But here you have the piezoelectric. That means stress has been developed because of lattice mismatch that gives rise to electric field in such a way that the top becomes negatively charged, the bottom becomes positively charged. So now it turns out that these particular polarization, spontaneous polarization, and the piezoelectric polarization, they play a huge role in regeneration of the something called as two-dimensional electron gas or the electron channel in these devices. Okay, and now you have to consider one more thing. If you have surface states here now. At this particular site, you have surface states of aluminum gallium nitride because you have not terminated it with any of the materials on the top. Just like you terminated the bonds in a gallium nitride with aluminum gallium nitride, this particular figure, if you don't terminate this particular sites, then there will be surface states. And those surface states, mostly donor type, they are positively charged and they give away the electrons. Okay, why they give away the electron? Again, because here you see that because of these particular, the electric field gets set up in this direction because you have positive, positive, negative, negative, electric field from positive to negative, and the electron will like to flow in this direction, in the opposite direction to that of the field. So what happens is when the electrons come away from these surface states, they settle here. This is LGAN. And it's a very interesting phenomena that happens. They settle at this particular location. And when you will see when you will draw the band diagram why they settle at this particular position, why they don't move further into the gallium nitride. Okay, one reason may be because there is an electric field is in this direction, then again the electron may want to go in this direction. But you will see from the band diagram there is a very little electric field remaining inside this particular gallium nitride towards the bulk. Because if this is, let's say, huge, let's say this is very thick, then that particular electric field gets shielded by other charges. Okay, let's say if you have a thick GAN, if you have a very thick GAN and this is let's say positive here, spontaneous polarization, this is spontaneous polarization negative, then because there are some intermediate charges also, the electric field lines which come from a positive charge, they end up at some other charges and only few lines will go to this negative charge. Basically electric field has electric field lines. You consider them as a field. Okay, so I should say weak field is basically remained. The weak field remains in case of a thick gallium nitride. If the thick gallium nitride layer is used, so that basically what it does is that there is no field inside this particular device. There's a very weak field inside the thick region of this gallium nitride. Okay, so now how you have to draw the energy band diagram of it? You do one thing. You take this device, you just rotate it anti-clockwise rotation by 90 degrees. That means you have L GAN here, you have GAN here, and you have to consider the charges as it is. You have to consider there are two charges here. There is negative because of spontaneous polarization, there is negative because of piezoelectric polarization. There is positive because of spontaneous polarization of L GAN, there is positive because of piezoelectric polarization of L GAN, and there is negative because of spontaneous polarization of GAN. Let's consider this as positive because of spontaneous polarization of the GAN, but this is far away. If you extrapolate this particular line and if you draw a figure like this, let me consider the y-axis as rho of x, which is the charge. Let's consider this as maybe x. So this is x, and x is the growth direction. This is the direction in which the materials are grown layer by layer. So layer by layer means if you take GaN, then you grow it layer by layer, the LGAN, and it forms the aluminum gallium nitride. That is how the growth is basically done. Atomic layer using something called as molecular beam epitaxy or molecular MOCVD, chemical vapor deposition. But that's not of your concern. You just have to understand the concept. So overall, now what you see, and also you have a positive donors. Let's call them as maybe ND donors, ND and small d. and capital D over it. Oh no, it's not a yeah, it's not just like a doping. These are donors which are positively charged, just like a plus Q and times Nd. These come from the surface states. And why they are positive? Because the electrons have left here and they have settled at this particular region. At this particular region. Now you have to draw the charges, just the charges. You have first plus Q times Nd, which is the donor, which is the donor charge. Just try to follow the color code. And then you have a negative charge because of spontaneous polarization of the algan and because of piezoelectric polarization of the algan. And you have again here a positive charge. You have positive charge and you have positive charge both because of piezoelectric polarization of algan and piezoelectric polarization, spontaneous polarization of the algan. And you also have slight negative charge. Let's consider it as negligible because that has been shielded because we are considering this layer to be thicker enough. Okay, so now what happens? You have to balance the charge in equilibrium. The charge on this side should be equivalent to charge on this side. You cannot have imbalance of charges, otherwise the current will flow by its own. Even if you don't apply any voltage, the current will start to flow if there is not imbalance of charge. That is what charge or current flow is. You create imbalance of charges on one side and the other side, and that results in the current flow. But here in the device, current doesn't flow by its own. That should not happen. So that's why always the charge neutrality has to be maintained. There has to be charge neutrality. Okay, charge neutrality means whatever positive charge is on this side, that has to be on this side. So when you consider that, let's consider in equilibrium, you have satisfied these particular two charges have satisfied each other. So now these positive charge has to be satisfied with something. So for it to satisfy, there has to be a negative charge here, or not this thing. There has to be a negative charge here. And this negative charge is basically those electrons. Why I draw it slightly inwards towards the GAN, it has certain reason. And where does this negative charge come from? That is the same electrons which come from surface states and that go here, settle at this particular position. Why it settles at this particular position? Because that is where the positive charges are present. Okay, so now the charge neutrality is maintained. A charge on this side is equal to charge on that side. You have the neutral condition. Now you draw the band diagram. Now, how you draw the band diagram? When you draw the band diagram, not the band diagram, I should say the electric field, first of all, you have to draw the electric field. So when you draw the electric field profile, you know that from the Poisson equation, dou E over dou X equals to rho X divided by epsilon. Okay, and you can integrate both sides. You can write dou E equals to rho X divided by epsilon into dx, integrate both sides, integrate both sides. So actually, you have to use something called as integral of d dot ds, which is the electric displacement vector equals to total charge. Maybe you can write it as q total. You can write this as electric field vector, which I showed you as epsilon times E plus polarization. Then you have ds, you have integral, that is the total charge. And when you separate these two components, you write it as epsilon E dot ds. Oh no, epsilon E dot ds plus integral P dot ds equals to total charge. That means this polarization component is actually a charge. It's just like behaving like a charge because there's a charge on right hand side. So the overall on the left hand side is whatever is on the left hand side, it's charge. Okay. So you have to consider it while basically writing the overall Maxwell equation for it. Now whatever you call as Poisson equation. Okay, so that particular polarization is also giving rise to this particular charges. Now, what you do is that whenever you do it, this particular this particular pink charge on the left hand side was satisfied has given an equal negative charges which has settled here because these electrons have come from those donors that they have donated the electrons and that has settled in this particular region which is shown in the downward arrow as pink. Okay, But now when you consider the overall charge, you see that this is overall positive because of huge piezoelectric and spontaneous polarization components, and this is overall negative again because of these polarization components. The donor charges are very small, yet they give rise to a very large number of electrons that we will see in the upcoming slides. So now you have an overall positive charge here, you have an overall negative charge here. This is a very simplistic picture, what I will say. If you draw the electric field profile, electric field is basically the integral of these charges. So if you have a delta function of charge, you integrate it, you get a unit step function. Delta function, you integrate it, you get a unit step function. That means, what does it mean? That means electric field is constant. That means electric field is constant. And it goes like this, goes like this. Okay. Now this is the electric field profile. When you what you do, you draw a potential profile, V of x. V of x is basically integral of E dot dx. Okay. And when you integrate it, you get a ramp like this, which is a linearly varying function, but a negative ramp with a negative slope. So this is the particular ramp or a slope of the potential. Basically, you get something like opposite direction because this is a potential. Because there was a negative charge earlier, so that negative and negative will go away. So this is the potential of this particular figure. And if you invert it, you write something like energy, which is minus q times potential. You get something like this. You have to invert it. So this is the exact band of the aluminum gallium nitride LGAN structure, LGAN. So that's why you see that it's a downhill. So any electron here will go down the hill and it will settle at this particular position. So this particular thing is the band of this. So now you have to extrapolate for the other valence band part. You have to again draw the similar line, which is exactly parallel to it, but down by the amount of down by the value of band gap, because this particular thing is the band gap. That part is not mostly done in the calculation because it is once you compute the conduction band, you shift it parallelly downwards by the value of band gap. That's it. And now you had a smaller band gap material of gallium nitride on this side. Gallium nitride. Let's consider this as Fermi level. So what happened? Now what happened is that there's a interesting thing here, that this particular thing bent it like this. Now this will try to basically move like this, and it will be joining this particular thing, and this will try to join this particular thing. So this is the overall schematic of how this band diagram looks like for a GAN-LGAN structure. Okay, now you see that this particular curve here, and not this one, not the upper one. This purplish curve is basically something called as energy band diagram of a LGAN-GAN structure. Now I'll try to just quickly summarize it. But the actually interesting part is right now, because it turns out that this particular, let me draw it like this. This is the particular potential, energy potential at this particular point. You see that this particular Fermi level goes through it. Whenever the Fermi level goes above the conduction band, it is something called as degenerate state, degenerate electron states. And that means there is a huge concentration of electrons at this particular point, at this particular point. Because the Fermi level is above the conduction band. This is conduction band, and Fermi level is above it. And it happens so because of higher potential on this side and a varying potential on this side. There are two potentials. One is from this side, another is from this side. It behaves as if it is just like a quantum well. What is a quantum well? It is just like a quantum well. Now, what is that? It sounds like a fancy term. It's just like you have a potential and you have another potential here. Something called as triangular potential. Triangular potential. You just kind of ignore the curvature of this particular thing, and you approximate it as a linearly varying potential on this side. you consider this as linearly varying instead of varying like a curve. Okay, why you consider it as linearly varying? Why not a curve? That has certain I should say reasons of its own. It's a very interesting problem. And what is a quantum well? You might have studied from your basic quantum mechanics, if even not a complicated quantum mechanics course. You know that if you have a potential V naught, and if you have some, let's say, some different material at this particular position, that gives rise to a very negative potential. Let's consider this as reference. If this is let's say this is an no, not let me just not draw it like this. Let me give you a very basic example. You know that if you have an atom, a positive charge, then if you have an electron coming towards it, the potential profile looks something like this. I showed it in the first lecture. Okay, that is the potential profile. That's the variation of the V as a function of x. That's the variation of the potential of this particular electron when it comes into the vicinity of the nucleus. Okay, and you see that this forms like a well for the electron. That means if the electron will come inside this region, it will form certain it can stay in this particular region. Okay, that is the simplistic example of a quantum well. It's not a realistic quantum well, but it's just like an atom. That is basically a kind of a potential for an electron. So quantum well is basically potential, a huge potential for an electron to stay. That makes it to stay there and cannot escape from that particular well. That's why it's called as well, because it traps the electrons. Now, similarly, if you have, let's say if you have, let's say if you have, if you have gallium arsenide and if you have aluminum arsenide, if you have aluminum arsenide, you have aluminum arsenide, which is a high band gap material. Its band gap is huge. I don't know the values. We are not concerned about the values. This is huge. On the other hand, gallium arsenide is lower band gap. So when you combine these materials together, just like this, you form a well type region here. This is a well, this is a well. And now what you do, let's say this is an a huge infinite well. That means if you consider this level as for example zero potential, for example, then you go down the hill, then it's a not zero potential. Let me draw it like this. That means this potential basically outside is huge. Let's consider this as infinite, and inside the potential is zero. That means outside the potential is going to be some positive value. Okay, so this particular is something like this. Okay, you have some positive potential here, but you have a zero potential here, and outside is infinite potential. If you draw V as a function of x, this is x. Okay, so it turns out if you now in this particular problem, in this well, if you have an electron, you keep an electron here inside this potential. Now electron has a charge. Okay, electron has mass. Now what happens to this electron when you keep it inside a well? Now to know that, you have to solve something called a Schrodinger equation. Schrodinger equation. I told you in the beginning of the lecture also in a previous session, I believe. When you solve the Schrodinger equation, which is h bar square by 2m minus h bar square by 2m dou square x by dou x square plus v psi equals to e psi, you have to solve this equation. If you consider the potential inside to be zero, this term will go because potential is zero. Now what you have to solve is minus h bar square by 2m dou square psi over dou x square equals to e psi. You bring this term towards this side, maybe that will easy make the problem easier. You write it as dou square psi over dou x square. Maybe you can write it as minus twice me divided by h bar square psi equals to 0. This is the differential equation you solve, which is del square psi minus k square psi equals to 0, where this k square is equivalent to not under root, this is twice me divided by h bar square. So this is a simple differential equation. You can solve and you get the psi solution value as some a sine of kx. This is the solution of this differential equation. Okay, just trying to make you realize what this thing is. So psi of x, you get some a sine of kx. This is the solution of this differential equation. So that means, and you know that whenever you solve a differential equation, you use the boundary conditions. Okay, what are the boundary conditions here? You cannot solve a differential equation without a boundary condition. You have to know what is happening at the boundaries of this, what is happening to the electron here, what's happening to the electron here. You know at this particular point and at this particular point, electron cannot move away from the potential because it's trapped inside the well, because outside the potential is infinite. Okay, it cannot leave it. It's inside the well. That means the wave function at this particular point, let's call it, let's call this point as 0, let's call this point as L. That means wave function at x equals to L goes to 0, and wave function at x equals to 0 goes to 0. These are the two boundary conditions which you need to use. When you use these boundary conditions, you get psi of x to be equivalent to a sine of n pi divided by L into x, where this k equals to n pi by L. Okay, that is the basic notion. So psi at x equals to 0 is basically 0. That means a sine of kx is equivalent to 0. That means sine of kx is equivalent to 0. That means kx is equals to n pi. That means this is L. Let's write it x. This is kx equals to n pi. At x equals to L, also the similar rule follows. So you can write it as kl equals to n pi. You can write k equals to n pi by L. So that is where it comes from. Now you see, you just plot this thing. N is basically an integer, which is 1, 2, 3, so on and so forth, positive integers. So when you take this well, you have infinite potential outside. This is infinite potential well, and you draw n equals to 1. For n equals to 1, you have a sine of pi x by L, which is the wave function at n equals to 1. So you have n equals to 1 level, and you have a half cycle of the sine. The full cycle of a sine looks like this. This is the half cycle of the sine. So you have this particular as the electron wave function. Similarly, if you plot for other levels, you get something like this, so on and so forth. Now, why is this important here? Now, that's what I want to highlight. Why is this important here? Here, instead of a square infinite well, you don't have a square infinite well. In high electron mobility transistors, you have something called as triangular well. Now, this is the potential V as a function of x. Let's consider this as x. And this is the potential profile. Now, if you consider on this side the potential is infinite, that means this line, this barrier is huge because this is Lgan. This is Lgan. And you consider only the pink region, this region, as a linearly varying potential. That means potential V of x is some maybe linear function of x, because it's straight line, linearly varying. So let's call it as V of x equals to A of x. It's a straight line. If this is V of x, this is x, this is a straight line. That is this pink line shown. Now you have to solve the Schrodinger equation considering potential V of x equals to A of x. When you write it, you can write minus h bar square by 2m dou square psi over dou x square plus A of x psi of x equals to E of psi. You have to solve now this equation. Now what is the complication in this equation? That is this particular variable x. Now you will have the overall equation as dou square psi over dou x square minus twice m e minus twice me divided by h bar square, and then you have A of x psi of x equals to 0. Did I write it correctly or not? No. This is twice me minus A of x psi of x equals to 0. This is the differential equation you need to solve. Now there's a problem because there's a variable x here also. Okay, and this is the differential equation in terms of x also. It turns out it's not easy to solve. There is no direct analytical solution possible for this equation. You have to solve it using certain techniques. You have to solve it. I don't know whether you know it or not, analytical or numerical techniques. And when you do it, when you solve this differential equation, what you get psi of x as a solution. And this is something called as Airy solution. Airy wave function solution. It's just the name of that solution given. But the important thing is, how does that look like? If this is a triangular well, this is huge, this is infinite huge, and this is the linearly varying well towards the gallium nitride. When you draw the energy levels, you draw the first energy level n equals to 1 here, and then n equals to 2 is here, n equals to 3 is here, 4, 5, 6, 7, so on and so forth. And you might notice as you go higher and higher in energy, the difference in the energy levels reduces. That is the specific, I should say, property of this triangular potential well. Or to okay, that's become coming because of the solution of this triangular potential well problem. And how does the wave function look like? It looks something like this. In n equals to 1, it looks something like this. In n equals to 2, it looks something like this. In n equals to 3, it looks something like this, similar to what it looks in a square potential well, except that this is an infinite well, but this is like a infinite well here, but this is like a finite well here. Okay, if we consider it infinite well on the left-hand side, then there will be no penetration of the wave function towards the left side or towards this side. There will be no penetration of wave function, and the wave function will look like this and this and this, and here it will be look like something like this. So you see that this is the wave function, this is the wave function here, this is the wave function here. So this is n equals to 1, n equals to 2, n equals to 3, so on and so forth. So what is this wave function representing now? So the mod of the wave function square, which is the probability of finding an electron in the well, is basically approximately equivalent to the charge density of the two-dimensional electron gas. Okay, so that is basically the notion of what is two-dimensional electron gas. And why it is two-dimensional? Because it is just like a well which is only existing in two dimensions, x and y. In the z dimension, it is confined. That means if you have a well, if you have a structure L GAN here, if you have GAN here, and if you have this 2D charges here, then they can move only. Let me draw it in three-dimensional fashion. This is 3D. This charge is present basically throughout in the layer, just at the interface of GAN L GAN. Okay, so this charge can move in this direction or this direction. It cannot move in this direction. It cannot move in Z direction. It cannot move. That is what is meant by 2D. Electron, electron is electron, and gas. Why it's called gas? Because it's just like electrons in a metal. Huge electron concentration in metal behaves like gas molecules with average kinetic energy as 3 by 2 kT, coming from the Boltzmann distribution and other things. Maybe you might remember studying from class 12th or class 11th, the average kinetic energy of the gas molecules, Boltzmann distribution, so on and so forth. So if you have very large number of molecules present, similar to if you have large electrons present at particular site, and if they are degenerate, they behave as if they are like gas molecules. They are huge in number, and you can average their energy out. Okay, that is the similar phenomena, similar notion why it's used as something called as electron gas. Why it's called as gas? It's not a gas. It's an electron, but it behaves as if it's a gas molecules. Okay, it's a very fascinating thing. And the final part, oh, it's already 7:32. What are we left with? Okay, this is covered. This is covered. I hope this is covered. Okay, now what we have? Now the final thing. Now you see from this particular let me try it again. You see from this particular triangular potential, well, when you draw the energy levels of this, and you see the spacing comes down as you go up and up in energy level. So this is n equals to 1, n equals to 2, n equals to 3, and let me draw this as this is L GAN, this is L GAN, this is GAN, this is here like this. Let me draw it like this to approximate. It's not exactly, but this is approximate. And the wave functions look now something like this. This. You see that the center of this wave function, the center of n equals to 1, is not exactly at the interface. It is away from the interface by few nanometers. This is something called a centroid of the wave function. This has a huge implication in these devices. Why? Because if this centroid of the wave function, which is basically the charge, that means the charge maximum peaks at somewhat like middle of the triangular potential well. It's not exactly at the interface. Okay, so it's just like a if you have a wall, let's say these are bricks, or if and its surface is rough, and if you are throwing a ball, let's not consider it as a wall. Let's consider a floor, and its surface is rough. And if you're throwing a ball, if the ball kind of moves on this rough floor, what is going to happen? It's going to face the friction. Can you just turn off the mic? Your mic is on, Lavanya. Can you just turn off the mic, please? Hello? Hello? Can you just turn off the mic? Your microphone is on. Okay, thanks. So what happens is that if you have a ball moving over this rough surface, then it will face friction. But if you move this ball in let's say somewhat at a distance from this particular rough surface, it's not going to face the friction at all. It will move on the surface as a kind of as without facing some much drag. That is the similar thing happens. This is the classical notion, obviously, but that is a similar thing what happens with electrons. If electron moves at this particular wall in this fashion, it will face more of the resistance because there are interfacial states at present at the green interface. But because electron maximum peaks here, so it moves in this particular fashion inside the channel, away from this particular wall, away from this interface. That reduces the interaction of this electron with the surface states, with the surfaces, with the interfaces. So that increases the mobility. So mobility increases, and that means current increases. That means it is beneficial for, I should say, high electromobility transistors and high frequency devices. That's just like an analogy I try to kind of frame. Okay, and now it turns out what are the other mechanisms that can slow it down? Well, the other mechanisms are if you have these electrons, they are moving in lattice. They are moving in lattice. That means if these are atoms, these are certain atoms, then they are connected to each other just like a spring, and they vibrate. Even at 0 Kelvin, they vibrate. And at room temperature, they vibrate a lot. Let's say at 300 Kelvin. So once, let's say, electron tries to move through this lattice, because they are vibrating, it tries to kind of change I shouldn't say change, I should say interact with this electron, because these are charges and they are interacting with these atoms, and it changes the energies of these particular electron. Let's say for a notion, for kind of a layman sense, if this particular atom is vibrating, if the electron is moving in this direction, electron now moves in this direction. And if another atom is vibrating, electron moves in this direction, and it moves in this direction. So instead of going through a straight path, electron moves in this curvy fashion. That basically impedes the motion of it and creates the resistance, something called as these are called as scattering events. And they can be created by either if there is impurity in it, or if there are phonons. Phonons are these lattice vibrations. Okay, so these lattice vibrations, which are basically the phonons, there are two types of it. One is called as acoustic phonon, the one is called as optical phonon. So you don't need to deal with the very in-depth concept of these, because these are very complicated concepts. You maybe won't be able to understand it in a depth in a very shorter scale of time here. So let's consider these are acoustic phonons are low frequency or low energy phonons, low energy vibrations, low frequency or low energy. And these optical phonons are high frequency vibrations or high energy phonons. Okay, so and this particularly becomes dominant because they are high energy and they becomes dominant in scattering mechanisms, and they scatter the electron. Okay, so now that is the fundamental story behind it. Now, what else are we remained with? Let's just try to jump to the questions. I will try to give you a rough idea about how to solve the questions because we are left with maybe only a couple of maybe 10, 20 minutes. So we have to first of all view the questions. The questions say that if you have a p-n junction with negligible valence band discontinuity and assume that diffusion coefficients are, first of all, you have p-n junction and it's abrupt. I told you what is abrupt junction. Abrupt junction means the charges, the depletion charges are going to look like something like this. It's an abrupt junction. Okay, and it's given that the valence band discontinuity is equivalent to zero, negligible, and the diffusion coefficient, which is dE, diffusion coefficient for electron and diffusion coefficient for holes, they are equal. That means dE equals to dH, and diffusion lengths, which is LE equals to LH. Now, what are these quantities? This diffusion length is the length which electron travels before it kind of diffuses or recombines with the hole. Let's say if this is a p-n junction. This is positive, 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 negative, 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 negative. These are depletion charges. If electron is going from this end to this end, hole is going from this end to this end in equilibrium. If you apply a positive bias, then what is going to happen? The electron coming from this end to this end will phase the holes and it will try to recombine. Similarly, holes going from this end to this end will phase the electron and will try to recombine. So the length they travel before recombining is the diffusion length. So they are considered here to be equal. Okay. Now what do we have to find? We have to find the ratio of electron to the hole current. I believe so. The conduction band discontinuity has been given, which is delta EC, and the ratio of electron to hole current is has to be obtained at 50 degrees centigrade, which you have to convert it into Kelvin. That is 323 Kelvin approximate. Yeah, that is 323. And all of the things are given. Boltzmann constant has been given as 1.23 into 10 to the power minus 23 meter square kilogram second square Kelvin. So basically this meter square kilogram second square is actually joule. It's a unit of energy because energy is half of mv square, which is kinetic energy. So m has units of kilogram, velocity has unit of meter per second. This is square, so you get kilogram meter square per second square. So this is energy. So that means the Boltzmann constant is 1.23 into 10 to the power minus 23 joule Kelvin. This is the Boltzmann constant he is talking about. So when you do it, you will get you have a relation between electron current and a hole current, which is basically dE by dH, LE by LH, and D over NA into e to the power minus delta EC divided by KBT, which is the relation of the electron concentration, electron current to the hole current, depending upon these parameters which have been given. Everything is given. So you just have to put it, which is ND over NA e to the power minus delta conduction band discontinuity KBT. So when you solve this particular thing, you have to solve this particular equation, which is very easy. You get IE by IH to be approximately equivalent to, I guess, 0.05 is the correct solution of it. Yeah, you get approximately equal to 0.05. So you have to solve it. That means electron current is approximately 0.05 times the hole current. That means it's much, much smaller than the hole current. So that is the first question. The second question, again, you need to see from the things which I have taught in the previous section. So now what we have. So this is the problem this is the problem basically which I try to discuss in my tutorials in my previous slides. So you have a heterostructure band diagram given. All of the things are given. The energy gap Eg1 of this has been given. Eg2 has been given. The electron affinity of this semiconductor, let's call it chi S1, has been given. This is chi S2, let's call it 3.8. It has been given. Fermi potential has been given. The Fermi potential here has also been given. Note that this looks like n-type because the Because the Fermi level is closer to conduction band. This also looks like n-type because the Fermi level is closer to the conduction band. So now you have to, if you combine these two and you draw the band diagram of this particular thing, how you draw it, you consider the line, you consider this point as here and this point as here, static. They don't have to move. This point as here, this point as here. Now, because this Fermi level is greater than this red Fermi level, that means the electron will move from this to this side. In doing so, that means this Fermi level will go down, this Fermi level will go up. Okay. While doing so, what is going to happen when the left-hand side will move up? Let me extrapolate this thing. And the left-hand side will move up. This is going to, this particular point is going to move like something like this. And this particular point is going to move like this because this particular end has been risen up. And in equilibrium, the Fermi level will be aligned. So let's draw the Fermi level. And these particular points will move down on this side. They have to go down. That means this particular point was above here. This particular point was just like here. That means you have a band bending on this side as this, and you have a band bending on this side as this, and you have to join these particular things. Again, you have to always make sure that in the bulk they remain same. That means Fermi level will be somewhere like here because this in the bulk does not have to change. If it was 0.25 eV, it will remain 0.25, and this is 0.15 eV. So that is the exact band diagram which will be shown. Now, what is going to happen to the vacuum level? For the simplest scenario, we consider the vacuum level to remain the same because all of these chi s1, chi s2 have to remain the same. That means this particular is chi s1, and from this red dot to this is chi s2. They are going to remain the same because these are the material parameters. Now you have to select one point, select a particular point, go in a loop, and sum over all the voltages. Okay, let's consider this particular point. You go here, then you go here, then you come down here, again here, and you sum over all the voltages. Basically, you have to compute the built-in voltages, which is basically this VB1, and this thing again here is, let's say VB2, which is basically this particular bend, this particular thing. Let me draw it using a different one. This particular thing. You have to compute the built-in voltage. Using the same procedure, you have to move it in a loop and sum over all the voltage to zero. Okay. When you do so, you can write, starting from this particular point, you can write 0.15 electron volt, okay, plus VB1, which is the built-in potential on this particular side, minus delta conduction band offset. What is the conduction band offset? This is the conduction band offset, delta EC. Okay, and you can write it as plus VB2, which is on the which when we are moving on to the other side. Okay, so we are moving, basically the path is like, let me show it in orange color. This, then moving on to this side. Then you have to go down by this side, this end. Okay, this, then this. Okay, that is the particular or best path in order to complete the loop. And then there is maybe whatever we have given. This is in energy gap is also given 4 electron volt. And we will move down as 4 electron volt because down will consider as negative, up will consider to be positive. And plus 3.75 is basically this difference, which is 4 minus 0.25. And it turns out when we have to compute VB1 plus VB2. So you do the computation, you bring all of the things here, you get what is happening? 0.10 plus delta EC because delta EC is unknown. Delta EC is this thing. Now, how do you compute delta EC? Delta EC is basically chi S2 minus chi S1, the difference in the electron affinities of it, which is basically 3.8 minus 3, which is 0.8. So that means you get VB1 plus VB2 as 0.90, which is the exact answer of this question. So that is the basic notion of the how you draw the band diagram of it. So you have to look at this particular example over and over again in order to understand what is the basic concept of drawing the band diagram of it. Now, over to this question. Both of the semiconductors have same electron mass, same electron effective mass. So effective mass is same, and assume 100% ionization. That means the effective mass on this side is equivalent to effective mass on this side. Which of the following statement is correct? Basically, it's the previous band diagram which is again shown. So the first is saying A is having higher concentration of electrons than B. Why is that the case? That's not, I believe that's not correct because this particular difference is same on both the sides. So they both have same electrons. Okay. B has higher concentration of electrons. No, because the Fermi potential is same. EC minus EF is same on both the sides. So it cannot have different number of electrons. On forming a heterojunction, their Fermi levels will not align at equilibrium since they have same free electron concentration. This is wrong because at equilibrium, Fermi level always aligns. This is to ensure net flow is zero in equilibrium. On both A and B will have same electron concentration since they have both same effective mass and difference between conduction band edge and Fermi level is same. That is the exact answer. Both will have same concentration of electrons because first they have same effective mass of the electron. Now, how does the effective mass play a role in having different number of electrons? That is something very interesting to look into, and maybe we will discuss that in the next lecture because we are running short of time. But the differences in the Fermi levels or the Fermi potential is same on both the sides. That is, Fermi level is at the same level on both the sides. That is marking it. That is indicating that you have same equal number of concentrations on both the sides. Okay, so that is the answer of this question. And select the correct statement. We cannot form a heterojunction by growth of arbitrary materials. That is true. You cannot form it because you know that there is a lattice mismatch. And if there is lattice mismatch, then you cannot grow any arbitrary material or over the other material. You can form a heterojunction between two arbitrary materials by growth and it does not need to be crystalline. This is wrong. You cannot form a heterojunction between two devices by any arbitrary method or arbitrary material. We can form a heterojunction between two materials of the same family by growth and it needs to be crystalline for RF devices. Yes, it's absolutely true. If it's from the same family is just like having the same crystal structure. Okay, just like there is a family called as wurtzite. Basically, the GaN, aluminum nitride, L-GaN, they belong to this particular family. And if you just search online, you can basically see the structure of this particular wurtzite. It's just like a hexagonal, stretch type of hexagonal structure. During the growth of heterojunction, lattice mismatch plays an important role. Absolutely, we discussed about it. How does the lattice mismatch play a role? If this is, let's say, lattice constant 1, this is lattice constant 2, then it depends upon the lattice constant whether there will be tensile stress or whether it will be compressive stress. Okay, so this is the answer of these two are the answer of this question. So that is the particular thing about. So we have discussed it in depth in the previous slides. In a graded heterojunction, again, a graded heterojunction is something like this, Okay, there can be a smooth variation of both conduction and valence band without any discontinuity. Absolutely. There can be smooth variation of either conduction band or valence, but this is also true. The force due to internal electric field experienced by the electrons are always in the same direction without any external bias. The forces due to internal electric field experienced this is the correct answer because you see that the electric field here is in this direction, electric field is in this direction. So the electron will face the force in this direction, the hole may feel the force in this direction. Okay. So the electric field directions may be different. The holes may feel the force in the different direction as well as in the same direction, depending upon if you have, let's say, a graded junction looking like this, maybe this, then electrons will feel the force in this direction. And holes may not go anywhere because there is not any bending in the structure. So this is the correct answer of this question. Maybe this part, and this part. Okay, there are multiple select answers. So this is the one such example. where there is a bending in the conduction band, but there is no bending in the valence band, you see? And how can you make it, how can you tailor this material? You can make this material by, let's say, selecting a particular material here of some EG band gap, and then go on increasing the band gap, keeping this valence band as constant. That means this band gap is increasing, it's increasing, it's increasing. Okay, so it can be made possible by grading it from x equals to 0 to x equals to L with another semiconductor, absolutely, of lower band gap with decreasing mole fraction. Okay, so mole fraction has to decrease. That means if it is, let's say, some A x B 1 minus x, then x decreases, the EG also decreases. If x increases, the EG also increases. So accordingly, you can tailor the mole fraction of the particular semiconductor, mole fraction of the particular element in order to tailor the band gap of it. Okay, just like just like you had two structures, if you change the x fraction of it, if you increase the x, the band gap increases. Similarly, you can do it here. Okay, that is the exact answer of this question. Which of the following quantities cannot be linearly extrapolated by Vegor's law? Vegor's law is just like if you have, let's say, A of x, B of 1 minus x type of structure, where x is the mole fraction, then you can write the band gap as x into maybe some band gap of A minus 1 minus x times the band gap of B plus some other parameter alpha. This is just like some equation or a empirical equation, what you call a mathematical equation which you can use to approximately know the band gap of the overall material if you know the mole fraction. That is the simple thing. But it turns out it does not work good for band gap. It works good for lattice constant, for dielectric constants, for effective masses, but not for the band gap, because for band gap, the band gap varies non-linearly with this mole fraction. And you have to consider this curvature, nonlinear curvature, in using this particular parameter, which is something called as Boeing parameter. Okay, so you can use the Vegor's law for all of these, but not for computing the band gap. Okay, that is the limitation of it. For a quantum confinement in a quantum well structure, the width of the well must be less than it must be less than the de Broglie wavelength. You remember from your class 12 physics, we studied about dual nature of matter, dual nature of matter. Dual nature of matter, you studied about something called as de Broglie wavelength, de Broglie wavelength, de Broglie wavelength, which was basically the wavelength is equals to h over p, where this is equal to h over mv, or you can write it as h over under root of twice m electron energy. Okay, so if you have if you have a very small mass, any particle having small mass, it will have a huge wavelength. And if you have a large mass, it will have smaller wavelength. And this was basically the starting point of the dual nature of matter. Okay, so that means everything in this universe is basically having a dual nature. Even we are having dual nature, but that is the only thing is that we are having a very huge mass. And if you put our mass into this equation, you can get to know your wavelength. So you can compute your wavelength. But if you put the electron's mass here, you can compute the electron's wavelength. And it turns out that the wavelength of the electron becomes significant only, or I should say, if you have an electron present in an energy level, you can treat it as a particle, you can treat it as a wave. No doubt, you can treat it as a particle, you can treat it as a wave. But what decides whether it is a particle or whether it's a wave? It is this particular dimension in which it is placed. Let's call it d, the I should say thickness of this barrier. If this thickness is of the order of lambda, which is the de Broglie wavelength, then the electron behaves as a wave. It's weird. That's how we show the wave function in the n equals to 1 of a quantum well. This is a wave function, which is a probability of finding the electron. The mod psi square gives the probability. This is just like a intrinsically you call it as wave function. So that is a function, but it's a wave function. Okay. So you have to consider the wave nature of the electron. And what is the wave nature of the electron? It's just the probabilistic. This picture is basically showing you that there is a maximum probability of electron to be found at the middle, but sometimes you can see the electron here, you can see it here, you can see it anywhere in the well. It just depends upon your measurement. When you measure it, you can see it anywhere in the well. But if you let's say increase the dimension of this well, let's say you make it like this, and you make d to be much much greater than lambda, you can have an electron as a particle, which is a classical entity, and you have to treat it as a particle. You have to apply the Newton's equation, Newton's laws. Maybe you have to write, you can write all of the Newton's equation, F equals to ma over it. Maybe you can write F equals to dp by dt, which is the rate of change of momentum. Although this is also applicable in quantum regime, but you can write all of the Newton's equation, classical equations for it. But for this picture, that's why we solved the Schrodinger equation for it. Because Schrodinger equation is a wave equation. It's just Schrodinger, that's why it's called a Schrodinger wave equation. And it is only applicable if you consider electron to be a wave, not as a particle. You cannot solve Schrodinger equation for it. Absolutely not. Okay, you have to solve the classical problem by using Newton's equation. Maybe you have to compute its trajectory just like a ball, and you can use v equals to u plus at. You can use s equals to, maybe you can use those equations of the motion, v square minus u square equals to twice as. All of those equations you can use in order to understand its dynamics, how it's moving inside this region. That is what gives rise to this quantum confinement effects. So that's why this particular parameter is a very important parameter. Make it, whenever you make the thickness of a barrier, you have to consider that it has to be of the order of wavelength of the electrons. Otherwise, you won't get any quantum confinement effects, or you cannot treat electron as a wave rather. And for L-GaN, question number 9 is for L-GaN GaN Woodside heterostructures, we have to select the option. So again, I showed you in L-GaN GaN the 2D electron gas is formed here. It comes because of the donor charges which give their electrons, and they settle at this particular position, which forms the 2D electron gas. So the donor surface states give rise to the 2D, and polarization helps in forming the 2D. Also because I showed you that there is a plus polarization charge here. There's plus spontaneously polarization charge here. This is piezo polarization, spontaneous polarization. There is minus pz, there is minus sigma spontaneous polarization charge here. So the polarization charge also helps in forming the 2D, but it's not necessary. Okay, because it enhances the field also. You can see that this overall this positive, this is overall now negative. Electric field will be in this direction, so the electron will move in this direction, down. So if you remove the polarization components here, not this, if you remove this component, still there will be field. It will be slightly less, but still there will be field. But combination of both spontaneous polarization and piezoelectric polarization enhances the 2D electron gas density. So you get a huge electron density in this particular, what you call as quantum well, the 2D electron gas. Okay. All right. So now, in which of the following does the barrier exhibit zero polarization? I believe you have to study it from different material perspective. I believe it is indium aluminum nitride and indium gallium and gallium nitride. So there is zero polarization in these particular structures, because it's almost as if it's lattice matched, as well as all other things are there. The lattice constant of both of the indium aluminum nitride and gallium nitride, they match. As a result, there is net zero polarization, negligible polarization. And which heterojunction doesn't have the formation of 2D electron gas? And you will see that it will be indium aluminum nitride and gallium nitride. Okay, I believe here the lattice match between indium gallium nitride and gallium nitride, and indium aluminum nitride and gallium nitride has the it doesn't have the formation of the 2D electron gas, because the energy band diagram in it looks something like this. No, not like this. It looks something like maybe this. That means you don't have any formation of the 2D electron gas. But some people are considering it to be maybe useful for something called as 2D hole gas. For electron, this acts like a potential confinement. You can have electrons here, but for holes, you should have it opposite way. That means it should look like something like, not this like, it should look something like this and this. If it is something like this, it will be 2D whole gas. Yeah, I know the time is over. You can just leave. It will be recorded in the YouTube. I'll just cover the question answer session. So this will be something called as 2D whole gas. There will be hole density, but which will be huge. But because why don't we like to play with holes? Because it is slower. Mobility of holes is much smaller than mobility of electrons. And as a result, the current because of that device which is hole operating will be much less than the device which is electron operating. But why is it important then? Why do we want to make a 2D hole gas? Why do we want a device in which the channel has holes? It is because you want to make something called as CMOS. CMOS is a device, complementary metal oxide semiconductor. This is the backbone of digital circuits. Digital circuits, where you play with ones and zeros. So it looks something like this. If you have a this is something called as PMOS. This is something called as NMOS. Here in this region, the channel, there are holes, and in this channel, there are electrons. So this is a MOSFET. This is metal layer on top. This is oxide, and this is semiconductor. That is what is exactly shown here. Okay. Then the red regions, the green region is basically the green and red regions are basically the green region is if there are electrons in the channel, and red region if there are holes in the channel as a moving charges. Okay, so you want to make it because you can make digital logic circuits using you can make AND gate, you can make NAND gate, you can make NOT gate. So this basically what I showed here is acting it can act like a NOT gate. If you give a signal 1 here, you will get a signal 0 here. That means it's like a NOT gate. If you give 1, you get 0, you give 0, you get 1. This is a circuit level representation of device. So you go from a quantum well to the circuit to the digital element, then you combine those digital elements one by one, and that is the fascinating part of it. Okay, now moving on to the question 12, you have the scattering mechanisms. I told you that the optical scattering will be much greater than the acoustic phonon scattering. Now, what is that? That's a very in-depth physics present in. Maybe in the future lectures we will talk about briefly about these particular scattering mechanisms, because that is exactly what my research topic is in order to understand these scattering in high electromobility transistors. So this is basically another question, which is the question that if you have a metallic pads and you have to compute the sheet resistance. Sheet resistance can be computed basically by 1 over n q mobility. That's it. You don't need anything else because you know the conductivity is n q mu. Okay, if this is the conductivity, yes, you know the conductivity is n q times mu, and you can play with this conductivity. You can play with the you can write it as 1 over inverse, and you get the basically the resistivity. Okay, and you have to note that the unit of this is particularly ohm per square. This is the unit convention used in the literature of these. So if you have two metal pads, where this is the width of the metal pad, 50 micrometers. These are 4 micrometers apart, and you are given the concentration, which is N. You are given mu. What else you need? You don't need anything else. You can compute the RSH. You get the value between 27 to 28. Maybe into 10 to the power 3 is also there. That is the value you will get. So that is the notion of it. But you have to consider one thing that, yeah, that's it. I believe that's it. So maybe we will discuss much more about it because we are overshooting the time right now. Okay, so it was a long session, and okay, is anyone present in the meeting? Yes, Sushant, do you have a question?
Uh, yeah, good afternoon. Just wanted to tell you, will this video be uploaded to that
Yes,
portal?
yeah. It will be uploaded on the YouTube as well, and you will get the link in that Google Sheet.
So because certain sections I actually missed,
Yeah.
so I
That's
I want to
absolutely
go
fine.
back and see those sections.
You can see it at your ease on the YouTube. Okay,
Okay. Okay, fine.
okay,
Thanks. It was very useful for me. I'll
okay.
I'll continue
Are
with it.
you a student, or you have not introduced yourself in the first session?
Actually, I was not there. I am doing my research from IIT Gandhinagar. My
Okay.
field would be HEMT only.
Who is your
So
supervisor?
I've just started and good. Yeah, he's Professor Mohapatra, Professor Nihar Ranjan Mohapatra.
Oh, nice. Okay, I know him. Okay, that's good.
Mhm.
Okay, fine. Thank you.
So my coursework is on, and this course would be a
Okay.
part. Yeah, yeah. Thank you.
Okay, sure. Thank you. Nice to meet you. See you again.